The journey starts with the most fundamental sensation we experience. It is that constant downward tug we feel beneath the soles of our feet as we stand upon the surface of the earth. From the time we are children, we are taught that this invisible pull is called gravity. We are taught that it originates from mass. We learn that our Earth possesses mass. We learn that the sun possesses mass. We learn that the distant black holes lurking in the dark possess mass. And because they have mass, they all exert gravity. Our intuition is sculpted by the image of apples dropping from tree branches, by the ocean tides rising and falling back, and by the absolute certainty that whatever goes up is destined to come down. To the majority of us, gravity is simply an invisible tether that binds us to the ground and binds the planets to their parent stars. It is Isaac Newton's falling apple, and it is the moon circling in the night sky. In this traditional picture, mass is everything. However, as the centuries passed and our scientific understanding deepened, cracks began to fracture this simple narrative. Newton had described gravity as a universal force of attraction between masses. Yet he could never truly explain how that attraction moved across the utter emptiness of space to take hold of another object. For Newton, mass was simultaneously the source of gravity and the substance of gravity. When Albert Einstein arrived centuries later with his general theory of relativity, he presented an idea so revolutionary that it completely dismantled the stage upon which Newton's physics had been performed. In the vision Einstein gave us, gravity was no longer a mysterious force transmitting between objects. Instead, it was the bending of space-time itself, a geometry of reality that is sculpted by the presence of matter and energy. And right here lies the mystery that shakes our common understanding. If gravity is actually the warping of space-time caused not only by matter, but also by energy, then the concept that mass alone rules the universe is incomplete. Light, radiation, pressure, and even the vacuum of empty space itself can curve the cosmos. This implies that the universe contains forms of gravity that emerge without any traditional mass at all. The sun holds us in place with its mass, certainly, but a single photon streaming from its fiery surface also adds to that gravity, even though that photon carries no rest mass whatsoever. This is not how most people visualize gravity. Our human senses cling desperately to things we can weigh and measure on a physical scale. Mass is something we can hold in our hands, lift up, drop down, and count. We imagine mass as the coin we must pay to buy the ticket of gravity. But nature accepts far more than just coins. Nature accepts energy, momentum, pressure, and even nothingness, transforming them all into the currency of curvature. To catch a glimpse of this profound truth, we must walk alongside Einstein, not just through the mathematics, but through the imagination that dared to wonder if space itself was capable of bending. The answer he found reshaped physics and compelled us to realize that the very notion of gravity existing without mass is not only possible, but it is essential to the story of the cosmos. Therefore, we set out on a journey, beginning with that everyday pull beneath our feet, tracing it into the mathematics of geometry, the shimmer of light, the pressure inside stars, the emptiness of space, and the ripples known as gravitational waves. In doing so, we will ask a question that sounds like heresy to our intuition, but is a requirement of modern physics. Can gravity exist without mass? In the silence that follows that question lies the origin of a new vision of reality. It is a vision that will carry us from the falling apple to the deepest truths of space-time itself. The apple falls, and we believe we understand why. The moon circles overhead, and we think the same rule applies. But when we look closer, when we measure with more care, and when we push our experiments into realms of extreme precision, the story becomes far stranger. Newton told us that mass attracts mass with a force that gets weaker as the distance grows. It was a simple law, and it worked well enough to guide ships across the oceans and to track planets across the centuries. Yet, there was always a shadow hanging over the theory, a sense of unease that even Newton himself confessed to. He asked how matter could possibly reach across the void of space to pull on other matter without some kind of medium, without some kind of mechanism connecting them. To him, this action at a distance was a profound mystery, one he admitted he could not explain. Einstein approached this problem from a completely different angle. He did not ask how the pull traveled. Instead, he asked whether there was a pull at all. What if objects were not tugging on one another across space, but were instead moving naturally along the curves of space itself? What if the presence of matter and energy bent the very fabric of reality, and motion was simply following the paths that those curves dictated? In that view, gravity is no longer a force in the Newtonian sense. It is geometry. Imagine a heavy ball pressing down into a rubber sheet. Marbles rolling nearby do not feel a force pulling them sideways. They simply follow the slope of the sheet as it curves down toward the ball. While this analogy is imperfect, it offers a glimpse of the elegance in Einstein's thought. Planets do not orbit the sun because the sun is pulling them across the emptiness. They orbit because the sun, by its mass and energy, has shaped space-time in such a way that the straightest possible paths are actually curved orbits. Here lies the critical point in Einstein's equations. What bends space-time is not only mass, but the entire stress-energy tensor, which is a grand accounting of mass, energy, momentum, and pressure. This means that light, even though it possesses no rest mass, contributes to the curvature. A box filled with light weighs more than an empty box because the photons inside carry energy, and energy possesses gravity. Even the pressure inside a star, the violent pressure of radiation pushing outward, also plays its role in shaping the surrounding space-time. Everyday intuition tells us to equate gravity strictly with mass. But general relativity forces us to expand that intuition. It demands that we consider not only the things we can weigh on bathroom scales, but also the momentum of radiation, the stress of fields, and the latent energy of the vacuum. The fabric of space-time does not discriminate. It curves in response to everything that carries energy or stress. And so the story grows more complex and more beautiful. The sun holds the Earth in orbit not only through its vast mass, but also through the energy of its radiation and the internal pressure of its core. A neutron star bends space-time not only because it is dense with matter, but because the pressure within its heart is so extreme that the pressure itself becomes a dominant source of gravity. Even light itself, streaming weightless across the cosmos, can bend space enough to deflect the paths of other light. This truth confronts our senses with a paradox. How can something without mass weigh upon the universe? How can light, which never comes to rest, create the same kind of curvature as stone or iron? Yet this paradox is resolved in Einstein's insight. What matters is not mass alone, but energy. And energy appears in many forms. Sometimes it is locked into rest mass, as in a rock. Sometimes it is set free as radiation, as in light. Sometimes it exists as pressure or tension. In all cases, space-time listens. If we could step back and view the universe as a great tapestry, we would see matter and energy tugging and stretching and curving the weave in every place and in every form. The picture would be alive, not static. Stars shining, light streaming, waves rippling, even the void itself pressing outward. All of it composing the geometry we call gravity. This vision unsettles the common mind because it severs gravity from the narrow prison of mass alone. But it also opens the door to new mysteries. If gravity can come from energy without mass, then what else in the universe can shape space-time? Could empty space itself have weight? Could a pulse of light create a ripple of gravity strong enough to measure? Could waves of pure curvature travel across the cosmos with no mass at all, only energy? To answer these questions, we must go deeper into Einstein's theory, peeling away each layer of intuition, following each thread of consequence. The question that began with an apple falling leads now to the very foundations of reality. When the question is asked plainly, can gravity exist without mass? The instinctive answer is to deny it. Our lives are lived in the company of mass. We lift objects, we drop them, we weigh them, we build our entire world from them. Gravity feels like an agreement between solid things. Yet when Einstein replaced force with curvature, he made that instinct incomplete. If spacetime itself is the stage, then anything that carries energy or stress can bend the stage. Mass is one actor, but it is not the only one. To see how deeply this idea runs, consider light again. A single photon is almost impossible to imagine as heavy. It slips through our skin. It glances off mirrors. It dances across the void. Yet gather many photons together in a mirrored box, and you find that the box is harder to lift than before. The trapped light contributes to its weight. That weight is not a trick of measurement. It is real. It means the photons, massless as they are, create a gravitational field. The consequence is staggering. A beam of light traveling through the cosmos, though faint in comparison with the pull of stars, does in fact curve space-time. In theory, two beams of light could even attract each other gravitationally, their paths subtly bending as they cross. These effects are vanishingly small to measure, but the principle is undeniable. Light has no rest mass. Yet light makes gravity, and light is not alone. Pressure itself, the invisible push of particles crowding against one another, has weight. Momentum flux, the transfer of motion through a medium, has weight. Even the stress in a field has weight. The stress-energy tensor accounts for it all, and space-time bends accordingly. The more carefully we examine Einstein's equations, the more they insist that gravity is democratic. It listens to all forms of energy, not only the familiar coin of mass. This broadening of perspective transforms our understanding of the cosmos. It tells us that stars are not bound only by their matter, but also by the radiation inside them. It tells us that the early universe, flooded with light, was governed by the gravity of photons as much as by particles. It tells us that the empty vacuum, once thought to be nothing, may in fact be a reservoir of energy whose pressure steers the destiny of galaxies. And so the simple picture of mass pulling mass dissolves into a richer vision. Gravity is not a string tied between objects. It is the geometry of existence itself, sculpted by everything real, whether tangible or intangible. The apple falls not because mass alone rules, but because space-time, shaped by energy in all its forms, guides its path towards the Earth. The weight of the question presses upon us now with more meaning than before. Can gravity exist without mass? The answer is yes, though with a nuance that requires patience. Gravity can emerge from light, from pressure, from waves of curvature, even from the void. But in every case, it requires something. Energy, in one disguise or another, must always be present. Gravity without energy is impossible. We stand then at the threshold of a profound realization. Our everyday sense of mass as the sole architect of gravity is only the opening act. Beyond it lies a universe in which spacetime responds to light, to fields, to stress, and to the vacuum itself. Mass is important, but mass is not everything. The true weight of the question lies in the discovery that gravity is not only the pull of matter, but the shape of reality itself. From this realization, we step into the next stage of our journey, where Einstein's geometry becomes our guide. We will see how space-time curves, how the stress-energy tensor weaves its influence, and how even the most intangible forms can sculpt the cosmos. The illusion that gravity belongs only to mass has been broken. Ahead lies the deeper truth that gravity belongs to all that exists. Einstein's revolution was not merely a correction to Newton. It was a rewriting of the very language in which nature speaks. Newton had pictured a universe like a grand stage, vast and empty, upon which matter played out its drama. Forces acted across that stage, invisible threads pulling objects to and fro. But Einstein asked, what if the stage itself is not silent? What if space and time are not merely the background, but the very fabric of reality capable of bending, stretching, and rippling? In that leap of imagination, gravity ceased to be a force and became geometry. Imagine a planet orbiting a star. To Newton, the star exerts a pull, a force proportional to its mass and inversely proportional to the square of the distance. To Einstein, there is no pull at all. The star has curved spacetime, and the planet simply follows the straightest path it can within that curved geometry. To picture this, we imagine again the rubber sheet with a heavy ball pressing into it, though in truth, the reality is four-dimensional and beyond direct visualization. The marbles roll not because they are pulled, but because the sheet itself guides them. The beauty of the theory is that it answers Newton's unease. No longer is there a mysterious force acting across emptiness. There is only the geometry of spacetime and the movement of objects within it. Yet the deeper insight is what causes that geometry to curve. Einstein's field equations do not speak of mass alone. They speak of the stress-energy tensor, a mathematical object that holds within it every form of energy, momentum, pressure, and stress. Mass is only one part of this story. Light contributes. Pressure contributes. Momentum flux contributes. If the universe is a great stage, then every actor, even those without mass, can shape the floor upon which all motion takes place. To see how this changes our view, consider a star. In Newton's picture, the star bends space by virtue of its mass alone. In Einstein's picture, the star bends spacetime not only by its mass, but also by the intense radiation within its core, by the pressure of its plasma, and by the momentum of particles racing through its furnace. A neutron star bends spacetime so powerfully not merely because of its density, but also because the pressure inside it is beyond imagination. Every form of energy counts. The stage curves to the total balance of stress and energy, not just to the coins of mass. This explains why light itself can be bent by gravity. When photons skim the surface of the sun, their paths curve. This bending was first confirmed during a solar eclipse in 1919, when starlight passing near the sun was observed to shift. The experiment was hailed as a triumph for Einstein. But the reverse is equally true. Just as light can be bent by gravity, light itself can create gravity. It carries energy, and space-time curves in response. The bending is mutual. In this geometry, even the void is alive. The field equations allow for a constant term, the cosmological constant, which represents energy in empty space. Far from being an idle addition, this constant means the vacuum itself has weight. An idea that seemed strange in Einstein's day, but resonates deeply with modern cosmology. If the vacuum carries energy, then the geometry of spacetime includes its influence. The stage curves, even where there is no matter at all. Einstein's vision demands that we let go of our everyday anchors. Gravity is no longer a pull, no longer an invisible tether between masses. It is the shape of reality itself, sculpted by all that exists. The path of a planet, the bending of light, the ripple of waves across the cosmos. All are consequences of the geometry. Mass is only the beginning of the story. To live within this geometry is to experience gravity without ever seeing it. We walk across the Earth and feel a downward pull, but in Einstein's picture, there is no pull. We are simply following the curved paths dictated by spacetime, paths that press us toward the center of the Earth and are resisted by the ground beneath our feet. What we call weight is the ground pushing back against the straight path that spacetime demands. If the Earth were to vanish in an instant, we would not be pulled anywhere. We would simply follow the geodesics of empty spacetime, floating freely. Gravity is not a hand tugging us, but the structure that defines how we move. This is why Einstein often described his theory as a triumph of geometry. The field equations are like a conversation between matter, energy, and the fabric of the cosmos. On one side of the equation lies the stress-energy tensor, the ledger of all energy, mass, momentum, and pressure. On the other side lies the curvature of spacetime, written in the language of tensors that measure how space bends and twists. The equality between them is the law of nature. Spacetime tells matter how to move, and matter tells spacetime how to curve. This reciprocity is what makes the theory so radical. It means that nothing exists in isolation. Place energy anywhere in the universe, and the geometry reshapes to accommodate it. Remove that energy, and the geometry shifts again. The universe is a living fabric responsive to every presence, dynamic and supple. The illusion of emptiness is broken. Even the vacuum, if it carries energy, can curve the whole. In everyday terms, the distinction is subtle but profound. A Newtonian mind asks, how strong is the force between these two objects? An Einsteinian mind asks, what is the geometry in which these two objects move? The difference may seem mathematical, but it changes the very foundation of causality. In Newton's picture, gravity is instantaneous action at a distance. In Einstein's, the curvature propagates at the finite speed of light, ensuring that nothing in the universe outruns causality. The bending of spacetime carries information, and that information moves no faster than light itself. This is why general relativity explains phenomena that Newton could not. The precession of Mercury's orbit, the bending of light near the sun, and the delay of signals passing close to massive bodies. All these emerge naturally from the geometry. Newton's law could approximate them, but could not explain the why. Einstein's equations show that the why lies in the shape of spacetime. The elegance of this vision doesn't make it less strange. We are creatures of intuition, and intuition resists the idea that geometry itself can bend. We imagine space as a container, not as something that responds. Yet evidence forces us to accept it. The starlight shifted during the eclipse. The clock slowed in gravitational wells. The satellites above Earth correct their signals for curvature. Without Einstein's geometry, Our global positioning system devices would fail. Our predictions of cosmic motion would collapse. The theory has passed every test, and with each passing century, it grows more essential to our understanding. And still, the most unsettling consequence remains. Because the stress-energy tensor accounts for more than mass, the geometry can be shaped by entities without rest mass at all. This is not speculation. It is built into the equations. Light bends spacetime. Pressure bends spacetime. Even tension in a field bends spacetime. Geometry is universal, impartial, and all-encompassing. When we recognize this, the question sharpens. If mass is not required to bend spacetime, then what else can? Can a pulse of radiation, if concentrated enough, carve out its own well of gravity? Can waves of curvature travel without any mass involved? Can the very vacuum, quiet and invisible, hold the fate of galaxies in its pressure? These are not idle questions. They are the path to the deeper chapters of our story. The key lies in the recognition that spacetime itself is an active participant in the drama of the cosmos. It is not passive, not a mere container into which energy and matter are poured. It flexes, curves, and ripples. The orbits of planets, the fall of apples, the drift of galaxies are all choreographies dictated by this geometry. And since geometry is shaped not only by mass but by all forms of energy, the reach of gravity extends far beyond the weight of matter. This becomes clear when we trace the consequences of Einstein's equations to their limits. A star collapsing to form a black hole bends spacetime so severely that even light cannot escape. Yet what defines the black hole is not only the mass it contains, but the geometry it imprints on the universe around it. The event horizon is not a surface made of matter. It is a boundary in spacetime. This is the purest manifestation of Einstein's vision. Gravity has ceased to be a force and has become entirely geometry. But the same equations that describe black holes also describe more subtle situations. A star burning steadily contributes to curvature, not only with its mass, but with the radiation pressure in its core. A gas cloud drifting in space curves geometry not only by the particles it contains, but by the pressure among them. Even a beam of light, if intense enough, could in principle generate measurable curvature. The idea sounds like a thought experiment, but it is real in the mathematics. Perhaps the most profound case is the vacuum itself. In Einstein's time, he included a constant in his equations, a term that could allow for a static universe. Later, he called it his greatest mistake. Yet, modern cosmology has returned to it under the name of the cosmological constant. This constant represents the energy of empty space, the pressure of the vacuum. And if the vacuum has energy, it has gravity. Empty space is not nothing. It is an ocean of subtle energy whose weight influences the expansion of the cosmos. This realization forces us to reconsider the very idea of existence. If emptiness itself curves spacetime, then geometry is woven not only by matter, but by the deep fabric of reality. Our intuition rebels, but the data insists. The acceleration of the universe's expansion, measured by observing distant supernovae, testifies to the presence of this vacuum energy. The fate of galaxies, of stars, of all structure depends upon it. Thus, gravity without mass is no longer a hypothetical curiosity. It is the ruling principle of the cosmos. Light bends spacetime. Pressure bends spacetime. Even the void bends spacetime. Mass remains the most familiar and powerful source, but it is not the only one. Geometry is richer than our senses allow. And so, as we close this chapter, we see the full depth of Einstein's vision. Gravity is geometry. It is not the invisible force of Newton. though Newton's law was a brilliant approximation. It is the dialogue between energy in all its forms and the fabric of space-time. To ask if gravity can exist without mass is to ask if geometry can respond to energy without substance. The answer written in every corner of the equations is yes. Mass is one voice in the chorus. But the song of gravity is sung by all that carries energy, even light, even nothing. The transition is natural and inevitable. If light itself can bend space-time, then we must ask what it means for a universe in which radiation, momentum, and pressure flood the cosmos. What is gravity when the actors are weightless? The next step in our journey is to strip away mass entirely and examine the power of pure energy. Energy and mass are two sides of the same coin, though for most of history, they were seen as entirely separate. Mass was the substance of matter, the heaviness we could feel, weigh, and hold. Energy was the power of motion, the heat of fire, the light of the Sunday. They were different categories in the language of physics, one tied to matter, the other to activity. Then Einstein revealed that they were bound by a simple yet profound equation. Energy equals mass multiplied by the square of the speed of light. This single relation declared that mass and energy were not separate at all, but interchangeable expressions of the same fundamental reality. The consequence was staggering. A small amount of mass could be converted into a vast amount of energy, and pure energy could, in principle, create mass. The world saw this truth in the blaze of nuclear fire, where fragments of atoms released energy powerful enough to scar cities. But the equation is not only about destruction, it is about the unity of nature. Energy and mass are not rivals, but partners. And space-time listens to both. This means that energy without rest mass can still create gravity. Consider light. A photon has no rest mass. It is the archetype of the massless particle, moving always at the speed of light, never slowing, never stopping. Yet it carries energy. It carries momentum. When light strikes a surface, it pushes. This is radiation pressure. Subtle but real. And because it carries energy, light contributes to the curvature of space-time. A single photon's effect is unimaginably small, but in great numbers, the effect can be significant. The universe in its earliest moments was filled with radiation, a searing bath of photons flooding space. During that epoch, it was not mass that ruled the expansion, but energy in the form of light. The curvature of space-time was shaped by photons rushing everywhere. The gravitational influence of this massless radiation was so strong that it dictated how matter would later gather into galaxies. In that sense, light without mass carved the scaffolding of the universe. Even today, stars shine with photons that carry weight in Einstein's sense. A star is not only a ball of mass, but also a furnace of energy, and that energy curves the geometry around it. Neutron stars and black holes are extreme examples where energy densities are so immense that their contribution to gravity cannot be ignored. The principle is universal. Where there is energy, there is curvature, whether or not there is mass. This is why Einstein's theory does not speak merely of mass, but of stress energy. It recognizes that photons, though massless, are woven into the gravitational fabric. It recognizes that momentum, pressure, and even vacuum energy carry the power to bend spacetime. The distinction between mass and energy fades. What matters is the total ledger of energy in all forms. To understand this more deeply, let us imagine a thought experiment. Suppose we trap light in a mirrored box, filling it with photons bouncing endlessly within. The box is heavier when the light is inside. The trapped energy adds to its gravitational pull. If we set that box on a scale, it weighs more than when it is empty. The photons themselves have no rest mass, yet their energy counts. The universe keeps no separate accounts. It totals everything. This thought experiment is not a trick of imagination. It reveals the essence of general relativity. Gravity is not about the heaviness of objects in the way our hands perceive. It is about the content of energy, whether locked in matter or freed as light. And in this broader view, gravity can indeed exist without traditional mass. The cosmos is filled with actors that play this role, and their influence is profound. The question now sharpens. If energy without mass can bend spacetime, what does that mean for the grand structures of the universe? What role do photons and radiation play in shaping cosmic destiny? How does pure energy write its signature into the geometry of reality? To follow these questions, we must look at the way light itself becomes a gravitational source, pulling though it has no rest mass, curving though it carries no substance. When we think of light, we often imagine it as something intangible, something that cannot weigh upon the world. It passes through glass. It reflects from mirrors. It illuminates without seeming to push. Yet light has momentum, and momentum is proof of its physical presence. When photons strike a solar sail, they transfer momentum and slowly accelerate the craft forward. This is not metaphor, but physics. And if photons can impart momentum, they must carry energy. And if they carry energy, they must shape spacetime. In the language of relativity, a photon follows the path of a null geodesic, a curve that has no rest in time, but always moves at the speed of light. Along this path, the photon contributes to the stress-energy tensor. Each photon's contribution is minuscule, but photons are abundant. A beam of laser light contains an ocean of them, each carrying energy, each pressing upon the fabric of reality. When they are concentrated, their collective effect is no longer ignorable. This leads us to a startling realization. A region of space filled with light has gravity. A mirrored box containing photons weighs more because the trapped energy contributes to the gravitational mass. In principle, a beam of light itself can bend the path of another beam of light, not through electromagnetism, but through gravity. The interaction is unimaginably weak, but the mathematics of Einstein's field equations permits it. Gravity is impartial. It answers to energy, not merely to substance. The early universe testifies to this truth. In its first hundreds of thousands of years, matter was not dominant. Photons and neutrinos flooded the cosmos with radiation energy that dwarfed the mass of particles. The geometry of that early era was governed not by atoms, but by light. As the universe expanded and cooled, radiation diluted and matter came to dominate. But the imprint of that radiative epoch remains. The cosmic microwave background, faint radiation still visible today, carries the signature of those times. A whisper of the era when massless energy ruled the shape of space. This is not only a story of the past. In the core of every star, radiation energy contributes to gravity. The pressure of photons trapped within the star balances against the inward pull of collapse. But those photons also contribute to the star's curvature. A star is not merely the sum of its atoms. It is also the sum of the energy that courses through it. The geometry around it records both. We see echoes of this in black holes as well. The collapse that creates them is driven by gravity's relentless answer to both mass and energy. When energy is trapped so completely that it cannot escape, the geometry becomes extreme. A black hole's gravitational well is not a force exerted by mass alone, but the total accounting of all energy frozen into a curvature from which even light cannot climb. The lesson repeats itself at every scale. Energy without mass still bends space-time. Photons curve geometry. Pressure curves geometry. Momentum flux curves geometry. The universe does not ask whether energy comes with substance. It curves to whatever ledger is present. And this means that gravity without mass is not merely possible, it is everywhere. As we accept this, our view of the cosmos changes. We no longer imagine gravity as the sole privilege of matter. Instead, we see a universe in which light, radiation, and stress all share the power to sculpt reality. The simple picture of mass pulling mass dissolves into a richer vision where energy in every form is a sculptor of geometry. But the story is not finished. If photons can create gravity, then what happens when countless photons move together, filling regions of space with their restless energy? What strange consequences emerge when energy without mass becomes the architect of curvature? These questions lead us to explore not only light as a source of gravity, but also the extraordinary ways in which massless fields shape the universe itself. The imagination stirs when we think of gravity born not from matter, but from pure energy. If a box of light weighs more when filled, then light itself is a source of space-time curvature. Consider then a universe that in its earliest moments was filled almost entirely with radiation. This was not an age of stars or galaxies, not an age of matter at all, but an age of light. The cosmic plasma glowed so intensely that photons collided constantly with particles. And it was this ocean of energy that determined the geometry of the young cosmos. The very structure that later allowed galaxies to grow was carved by energy without mass. This influence is not only ancient. Even today, radiation contributes to the evolution of the universe. Neutrinos, nearly massless particles streaming through space in unimaginable numbers, carry energy that adds its weight to the cosmic balance. Starlight, though it seems delicate and intangible, is woven into the gravity of galaxies. Every photon adds its part, a whisper of curvature in the grand equation. The universe listens to them all. The principle becomes even more dramatic when we consider extreme thought experiments. Imagine constructing a perfectly reflective sphere and filling it with an immense pulse of laser light. The photons bounce endlessly, trapped inside. The sphere becomes heavier, not because we added any atoms, but because the trapped energy now counts toward its gravitational mass. In theory, if enough energy were trapped, the sphere could collapse into a black hole, even though its substance was nothing more than light confined. Such a vision pushes the limits of engineering beyond reason, but it illustrates the law of nature. Energy, in whatever form, has gravity. This realization forces us to reconsider our definition of emptiness and substance. A beam of light passing through space is not nothing. It is energy on the move, shaping geometry in its passage. A star is not simply matter, but also light streaming outward, light that contributes to the curvature around it. Even the early universe before atoms could exist was sculpted by photons alone. The human mind struggles with this because our senses equate gravity with weight, and weight with substance. We imagine lifting a rock and feeling its heaviness, and we imagine light as weightless, intangible. But the mathematics of relativity and the evidence of the cosmos say otherwise. Light is weightless only in the sense of lacking rest mass. In the deeper sense of energy, it is heavy indeed, and the universe bends to acknowledge it. The boundary between mass and energy is less like a wall and more like a veil. Under certain conditions, energy becomes mass, as when particles and antiparticles form from pure radiation. Under other conditions, mass becomes energy. As in nuclear reactions, the two are convertible, but both curve spacetime in their own right. Mass is only a form of energy, and energy is the more fundamental quantity. And so, when we ask if gravity can exist without mass, this chapter gives us the answer. Yes, it can. It does. It always has. The universe itself is proof. Gravity without mass is not an exception, but a rule woven into the equations from the beginning. Mass is only one expression of energy, but energy in every form bends space-time. This understanding leads us forward to the next mystery. If photons can pull, if light itself can weigh upon reality, what happens when those photons are gathered in vast numbers? Can light alone shape stars, galaxies, or even black holes? Can beams of radiation bend space enough to act as gravitational wells? These questions guide us into the next stage of our journey, where the gravity of photons becomes not only theory, but cosmic consequence. Light seems delicate to us, an illumination, a shimmer across surfaces, a warmth upon the skin. We do not imagine it as something heavy or forceful, and yet photons can push. They strike sails, they drive particles, they exert pressure. If they can push, then they can also pull through gravity. This is the strange consequence of Einstein's insight that energy is equivalent to mass, and that energy alone can curve spacetime. A photon carries no rest mass, yet its energy and momentum are undeniable, and the universe listens to that energy as faithfully as it listens to the weight of matter. To appreciate the depth of this truth, imagine a box filled with light. The photons race from wall to wall, bouncing endlessly. The box weighs more when the light is inside than when it is empty. This is not a metaphor or an illusion. The added weight is real, measurable, a manifestation of the photon's contribution to the stress-energy tensor. The photons themselves are massless, but together they increase the gravitational pull of the box. In principle, if the light inside were intense enough, the box could collapse into a black hole. Pure energy could create gravity strong enough to trap itself. This is not mere fantasy. It is a natural consequence of relativity. If mass and energy are equivalent, then there is no distinction in how spacetime responds. Energy curves spacetime, whether it is locked into particles or streaming as light. In the cosmos, where light floods every corner, the gravitational role of photons cannot be ignored. Consider the interior of a star. Photons born in nuclear reactions ricochet through the plasma for thousands of years before escaping into space. Their pressure pushes outward, counteracting the inward pull of gravity. Yet these same photons add to the star's gravity by virtue of their energy. A star's geometry is shaped not only by its atoms, but also by the light trapped within. Without photons, the balance of a star's life could not exist. With photons, the very curvature of spacetime is different. This extends to the early universe. When matter was still bound in plasma, photons roared through the cosmos, colliding constantly with particles. Their collective energy was the dominant source of gravity, shaping how the universe expanded. It was an epoch when photons, not atoms, pulled the strings of spacetime. Only later, as expansion cooled the cosmos, did matter rise to dominance. But the imprint of the photon's reign is written in the structure of galaxies and in the faint microwave background we still observe. And yet the thought lingers. Could we, in principle, generate gravity by creating light alone? If a powerful enough laser beam were concentrated, would it bend spacetime? The answer is yes, though the effect would be astonishingly small. To curve spacetime in any measurable way would require energies far beyond our technology. Beams of such intensity they could rival stars. Still, the principle holds. Photons pull. Light has weight. Radiation creates gravity. This realization changes how we see the universe. No longer is gravity the sole privilege of heavy masses. Even the weightless actors of the cosmos, the photons streaming endlessly through the void, contribute to the bending of space. The universe is filled not only with the pull of matter, but also with the silent weight of light. To understand the gravity of light, we must linger on the way photons behave. A photon cannot rest, cannot be weighed on a scale, cannot be slowed to stillness. It exists only in motion, always at the speed of light. Yet, when it strikes a surface, it imparts momentum, and momentum is mass-like in its effect on spacetime. When countless photons are gathered together, their collective energy becomes indistinguishable from mass in the way gravity responds. This is why a box of light weighs more, why radiation pressure contributes to a star's gravity, why photons that are individually massless can together shape the cosmos. There is a thought experiment that brings this to life. Imagine a perfectly reflective cube suspended in empty space, its walls so flawless that photons inside never escape. You shine a laser into it until it is filled with light, photons bouncing endlessly from one wall to the other. The box grows heavier, not because you added matter, but because you added energy. Place two such boxes side by side, and they would feel a greater attraction than if they were empty. The photons inside, trapped and weightless in themselves, now act as a source of curvature. Light has become gravity. This principle is not confined to thought experiments. In the hearts of stars, photons collide with plasma particles pushing outward. Their pressure is enormous, and it is a fundamental part of stellar structure. But the photons also contribute directly to the star's gravitational field. When astronomers calculate the mass of a star, they include the energy of the radiation inside. Without it, the equations of equilibrium would not hold. The life and death of stars are determined not only by the atoms they contain, but by the photons they emit. The effect of photons on spacetime is subtle, but the cosmos has had eons to amplify it. In the earliest times, before matter dominated, photons were the ruling source of gravity. They bent the universe into the shape we see today, guiding how matter clumped into filaments and voids. The cosmic microwave background is a fossil of that era, a whisper of the time when photons pulled more strongly than atoms. The galaxies and clusters that now span billions of light years owe their structure in part to the gravity of light, this dual role of photons as both passengers in the geometry and contributors to it is one of the profound symmetries of relativity. Light is guided by spacetime curvature. Yet, light also curves spacetime. When a photon grazes the edge of the sun, its path bends because of gravity. And at the same time, the photon's energy adds to the sun's own gravitational pull. It is a perfect reciprocity, a dialogue written into the fabric of the cosmos. The question remains whether humanity could ever harness this. Could we gather enough photons in one place to generate a measurable gravitational effect? In principle, yes. In practice, the amount of energy required is beyond our reach. The curvature produced by even the most powerful lasers is too small to detect. Only in stars and in the early universe does light achieve densities high enough for its gravity to matter. And yet the thought experiment reminds us that the line between matter and energy is thinner than we imagine. If photons can pull, then the universe is a web of countless invisible weights. Every beam of starlight, every flicker of radiation, every photon born in the nuclear furnaces of stars or in the silent decay of atoms contributes its grain of curvature to the cosmic whole. Gravity is not only the empire of massive bodies, but also the empire of light. If photons truly pull, then we are forced to look at light in a new way. We are used to thinking of it as a messenger, a traveler carrying information from stars to our eyes. We measure distances with it. We tell time with it. We illuminate the darkness with it. But in truth, light is also an architect, sculpting the curvature of spacetime as it moves. Every photon is both passenger and shaper, guided by geometry and contributing to geometry at once. The symmetry of this is astonishing. A beam of light curves when it passes near a massive star, and yet that very beam adds to the star's mass-energy content. Light obeys gravity, but light also generates gravity. This reciprocity shows that there is no hierarchy between mass and energy. There is only the ledger of total energy and momentum. And spacetime responds to the sum of it all. One might ask, could two beams of light in the emptiness of space bend one another? In principle, yes. Their gravitational fields would cause a minute deflection, so small it is beyond measurement with current instruments, but the effect is real in Einstein's mathematics. Light can curve light. In the searing chaos of the early universe, where photons filled every corner, such effects were not negligible. Photons influenced each other's paths, and the geometry they carved was the scaffolding upon which matter later assembled. This is the unseen power of radiation. It is not merely decoration upon the cosmos. It is part of its skeleton. The great filaments of galaxies, the voids between clusters, the very expansion of the universe itself were shaped by epochs in which light, though massless, was the primary sculptor of geometry. That imprint remains today in the cosmic microwave background, where tiny ripples tell the story of photons pulling upon spacetime. The thought experiments that seem fanciful, boxes filled with light, beams curving beams, are echoes of realities that have already played out on cosmic scales. Stars themselves are boxes filled with trapped photons. The early universe itself was a furnace where photons ruled. The principle is not a fantasy, but a fundamental law. Energy bends space, and light is energy. And yet there is a humility in this realization. For all our technology, for all the power of our lasers and reactors, we cannot come close to the scales at which photons generate measurable gravity. The cosmos achieves with ease what we can only imagine. The interiors of stars, the collapse of massive objects, the blaze of the early universe. These are the laboratories where light pulls as strongly as matter. Humanity can only observe and wonder. Still, the lesson is clear. Gravity is not confined to the weight of matter. It is the shared work of all energy, and photons are its most abundant contributors. Everywhere light travels, it writes its faint signature into the curvature of the cosmos. Every star, every quasar, every background photon from the birth of the universe is part of gravity's tapestry. And so the idea that light pulls is not metaphor, but reality. Photons, though massless, are participants in the dance of gravity. They may not weigh in the way we imagine, but they leave their mark upon the universe's shape. From this point forward, we cannot speak of gravity as the domain of matter alone. Light, too, has joined the story, bending spacetime with every step of its restless journey. This insight pushes us to broaden our gaze even further. If photons can create gravity, then so can other forms of massless energy. Pressure, momentum, and stress themselves are sources of curvature. What we think of as empty or intangible may in fact be heavy in the eyes of spacetime. To understand this, we must now turn to the very structure of Einstein's equations and see how momentum, flux, and pressure contribute to gravity as surely as mass or light. When Einstein wrote his field equations, he knew he was describing more than mass. The geometry of spacetime is shaped not by weight alone, but by the full accounting of energy in all its forms. This is why the right side of the equations is not a simple mass term, but the stress-energy tensor, a mathematical structure that holds within it energy density, pressure, momentum, and stress. Each is a participant in gravity's dialogue. Each can bend spacetime. It is easy to accept that mass curves space, and with some imagination, we can accept that light does the same. But pressure as gravity? Momentum flux as gravity? Stress in a field as gravity? These ideas are harder to see, harder to feel, but they are no less real. When a gas is heated and its pressure rises, that pressure contributes to the curvature around it. When radiation fills a star, its outward pressure does not only resist gravity, it also adds to gravity. Even in regions where no mass can be found, the energy of fields and their stresses can shape the stage upon which the universe moves. Imagine again the interior of a star. The atoms within are crushed by gravity, their collisions violent, their temperature soaring. Photons bounce endlessly, exerting pressure against collapse. Yet in the equations, that very pressure contributes to the star's gravitational pull. It is as if the resistance to gravity has itself become another source of gravity. The greater the pressure, the more intense the curvature. This is why neutron stars, with pressures billions of times higher than anything on Earth, create such extreme gravitational fields. The pressure is not incidental, it is central. Momentum flux plays its role as well. In a stream of particles, the flow of momentum through space has weight in the eyes of spacetime. Even if the particles are nearly massless, their flux is recorded in the stress-energy tensor. The geometry bends in response. Fields that carry tension or shear also curve spacetime. The universe does not ask whether these things can be held in the hand. It curves to the presence of energy wherever it hides. This principle reaches into the most abstract corners of physics. The stress-energy tensor can describe not only matter and radiation, but also the vacuum itself. If the vacuum carries energy, it carries pressure. And if it carries pressure, it curves spacetime. Thus, the very emptiness between galaxies has gravity not because of mass, not because of light, but because of stress and pressure built into the fabric of reality. The mind resists this because we are trained by experience. We feel weight when we lift an object. We do not feel the pressure of photons or the momentum of fields as weight. Yet, spacetime is impartial. It bends to all forms of energy without prejudice. The sun shines, and the light it emits has gravity. The Earth spins, and the momentum flux of its motion adds to the curvature. The vacuum hums with energy, and its pressure stretches the universe itself. This is the expansion of gravity's definition. It is no longer only the pull of matter, nor only the bending caused by light. It is the bending caused by pressure, stress, and motion. Gravity is geometry responding to the total balance of energy in every form. In this sense, even emptiness is heavy. Even resistance is weight. Even flux has curvature. From here, the path leads to the strangest implication of all. If pressure and stress can bend spacetime, then the vacuum itself, with its latent energy, can control the fate of the cosmos. What seems like nothing may in fact be the heaviest player of all. To grasp how pressure and momentum create gravity, we must lean into Einstein's mathematics. The stress-energy tensor is not a single number, but a grid of values, each one describing a way in which energy and momentum are distributed through space and time. Energy density appears in one place, pressure along each axis in another, momentum flux in yet another. Together they form a full description of how energy exists, moves, and interacts. Spacetime does not curve to mass alone. It curves to this entire account. Take pressure as the first example. In the furnace of a neutron star, pressures reach unimaginable scales, so immense that atomic nuclei collapse and electrons merge with protons to form neutrons. What holds the star up is not only degeneracy pressure, the quantum mechanical resistance of neutrons to being squeezed further, but also the outward push of radiation within. Yet the paradox is that the same pressure that resists collapse also deepens the curvature. Pressure contributes positively to gravity, so the more intense it becomes, the stronger the pull. This is why neutron stars balance on the knife's edge. Their own pressure is both their salvation and their burden, helping them stand against collapse, but also adding weight to the collapse itself. Momentum flux tells another part of the story. Imagine a river of particles rushing in one direction. Even if the particles are extremely light, the fact that momentum is flowing through a region means that energy is being transferred. In relativity, energy and momentum are inseparable. If momentum is moving, spacetime responds. This is why even radiation streaming through the cosmos contributes to gravity. The photons have no rest mass, but their momentum flux curves spacetime just as surely as their energy density does. Stress in fields is subtler, but equally important. A magnetic field stretched across a region has tension as though invisible lines are being pulled taut. That tension is energy, and energy has gravity. The same applies to electric fields, scalar fields, and the exotic fields invoked in theories beyond the standard model of physics. Wherever there is tension, stress, or flux, there is a contribution to the bending of space. The cumulative effect of these contributions is profound. The geometry of spacetime is not written only by stars and galaxies, but also by the invisible pressures and fluxes that permeate the cosmos. Radiation pressure inside stars alters their gravitational signatures. The flux of neutrinos racing through space adds to the total curvature. Even the tension of cosmic fields plays a role. The fabric of reality is sensitive to everything. The implications extend beyond the stars. In the early universe, pressure dominated. Radiation pressure and momentum flux from photons determined the rate of expansion, how matter clumped, and how geometry evolved. Without considering these effects, we could not explain the patterns imprinted in the cosmic microwave background. Those patterns are fossil records of pressure and momentum shaping spacetime. For us, accustomed to thinking of gravity as the domain of heavy masses, this is unsettling. Pressure feels intangible, momentum flux invisible, stress abstract. Yet relativity insists they are as real to spacetime as stone and iron. To ignore them is to misunderstand the foundation of gravity. And so we are led to a deeper truth. If even pressure and flux contribute to curvature, then nothing is too small or too abstract to weigh upon reality. The universe counts everything. It adds the mass of planets, the light of stars, the pressure of radiation, the momentum of streams, the stress of fields, and it curves accordingly. The stage has now been set for the strangest player of all. If fields and pressures we can see have gravity, what about the vacuum itself? Could nothingness have weight? Could the emptiness between galaxies be heavy enough to shape the fate of the cosmos? The mathematics says yes, and the observations confirm it. If pressure and momentum can shape spacetime, then emptiness itself must be questioned. What we call empty is rarely so. A vacuum is not an absence, but a seething field, a stage upon which quantum fluctuations flicker in and out of being. In Einstein's language, even this nothingness carries stress and energy, and therefore even this nothingness curves spacetime. The stress-energy tensor does not distinguish between the tangible and the intangible. It responds to everything that carries energy, including the invisible whisper of the vacuum. This idea, strange as it sounds, emerges naturally once pressure and momentum are accepted as gravitational sources. A photon bouncing in a star does not only resist collapse, it also deepens gravity. A stream of particles does not only move, it reshapes geometry with its flux. A magnetic field does not only push charges, it bends spacetime with its tension. If these things are true, then the vacuum itself, with its constant background of energy, must also play its role. And in fact, observations suggest it does. The accelerating expansion of the universe points to a form of pressure that is not tied to mass or radiation, but to space itself. It is as though the very emptiness between galaxies exerts a pressure outward, stretching the cosmos. This dark energy, as it has been named, behaves like a weightless field with negative pressure, a form of stress that dominates the universe today. Its gravity is peculiar, not pulling objects together, but pushing space apart. Yet it is gravity all the same, written into the geometry by pressure rather than by mass. The realization is profound. Gravity cannot be reduced to mass or even to light. It is the sum of all forms of energy and stress. The universe is not shaped only by stars and planets, but also by radiation, by pressure, by momentum flux, and by the vacuum itself. To imagine that only mass creates gravity is to see only a corner of the truth. The full picture is that space-time listens to everything. This truth is unsettling because it leaves us without simple intuition. We can hold a rock and feel its weight. We can imagine the mass of the Earth and the Sun. But we cannot hold pressure in our hands. We cannot lift a photon. We cannot weigh the vacuum. And yet each of these bends space-time as surely as matter does. Relativity demands that our vision of gravity be expanded beyond the limits of human senses. In this expanded vision, nothing is truly weightless. Photons curve geometry, pressure curves geometry, flux curves geometry, stress curves geometry. Even what we call nothing curves geometry. The cosmos is a fabric woven not only by the visible masses, but by the invisible energies that permeate every region. This leads us to the next chapter, where the strangest implication of all takes center stage. If the vacuum itself has energy, then empty space has weight. If empty space has weight, it can control the fate of the universe. The most powerful form of gravity may come not from stars, not from galaxies, not from light, but from the very nothingness that lies between. There is a strange silence at the edge of physics, a silence that whispers of emptiness. For centuries, nothing was thought to be the absence of everything, a blank canvas upon which matter and energy performed their roles. Space was void, and void was nothing. Yet in Einstein's equations, the void is not silent. It has weight, it has pressure, it has the power to bend space-time. Nothing, it turns out, is not nothing at all. This realization begins with the cosmological constant, the extra term Einstein added to his field equations in 1917. He sought a way to balance the pull of gravity and create a static universe, a universe neither expanding nor contracting. His constant was meant to be a kind of pressure in empty space, a hidden weight that would hold the cosmos steady. But when Edwin Hubble discovered the expansion of the universe, Einstein abandoned the constant and later called it his greatest mistake. The mistake was not in including the term, but in misunderstanding its role. The expansion was real, but so was the possibility that empty space carried energy. Decades later, astronomers discovered that the expansion of the universe is not slowing down as gravity pulls, but speeding up as though pushed by some hidden pressure. The cosmological constant returned. No longer an error, but a necessity. The vacuum itself, the emptiness between galaxies, was revealed as a source of gravity. To understand this, imagine space as a fabric that can stretch. If that fabric carries energy within itself, then as it stretches, the energy does not dilute like matter or radiation. It remains constant per volume. So the more space there is, the more total energy there becomes. This creates a pressure that pushes the universe apart. The effect is strange, for gravity has always seemed to be a pull, yet here it appears as a push. But in truth, both are the same. Gravity is curvature, and curvature can either pull objects together or drive them apart depending on the sign of the pressure. This is the weight of nothing. Empty space itself has a density, a pressure, a gravitational effect. It does not need mass, it does not need light, it does not need particles. The vacuum alone curves spacetime. This form of gravity, known as dark energy, now dominates the cosmos. Galaxies drift farther apart, not because of hidden masses, but because of the weight of the vacuum itself. The implications are staggering. What seems like nothing controls the fate of everything. Stars and galaxies may blaze for billions of years, but the expansion of the universe is determined not by them, but by the energy of emptiness. The final destiny of the cosmos, whether it expands forever, tears itself apart, or collapses back into fire, is written in the pressure of the vacuum. We are thus forced to abandon our last illusions about gravity. It is not the pull of matter alone. It is not even the influence of light and radiation alone. It is the curvature of space-time in response to energy, wherever it resides, even in the void. Nothing has weight. Nothing has power. Nothing shapes the universe. The thought that nothing has weight unsettles intuition. We are accustomed to linking gravity with things we can see and touch. A rock has gravity. A star has gravity. A black hole has gravity. But what of the spaces in between? What of the vast reaches between galaxies where no matter shines? Einstein's equations insist that even this emptiness cannot be ignored. If the vacuum contains energy, then space-time bends in response. To see why this matters, we look to the expansion of the cosmos. When Hubble measured distant galaxies nearly a century ago, he found that they were receding from us. The farther they were, the faster they fled. This suggested an expanding universe, a beginning in time, a big bang. For decades, astronomers assumed that gravity from matter would slow this expansion, perhaps even reverse it. Yet, in the 1990s, two teams of scientists studying supernovae found something astonishing. The universe was not slowing down, it was speeding up. Galaxies were not only fleeing, but accelerating away as though pushed by an invisible hand. The only explanation that fit was a hidden form of energy spread evenly through space, exerting negative pressure. In Einstein's equations, this appears naturally as the cosmological constant. In modern language, it is called dark energy. Its effect is subtle on small scales, but on the scale of billions of light years, it dominates. Today, observations suggest that nearly 70% of the total energy of the universe resides not in stars or galaxies, but in the vacuum itself. The fate of the cosmos is written not in the mass of matter, but in the gravity of nothing. The strangeness of this cannot be overstated. If you take a cube of space 1 meter on a side and remove all particles, all photons, all fields, what remains is not nothing. Quantum physics tells us that even the vacuum seethes with fluctuations. Pairs of particles flickering in and out of existence. This restless energy, though invisible, contributes to the density of space. And because density is energy, it bends spacetime. What we once called emptiness is a gravitational actor. The consequences ripple across cosmology. In the far future, if dark energy remains constant, galaxies beyond our local group will slip away beyond sight, carried faster than light by the swelling of space itself. Stars will burn out, black holes will fade, and the universe will become a cold, dark expanse of isolation, expanding forever under the weight of nothing. If instead dark energy grows stronger with time, the expansion will accelerate until even atoms are torn apart in a final big rip. If it weakens, the expansion may someday halt and reverse, collapsing into a fiery big crunch. The destiny of the cosmos is balanced upon the properties of emptiness. This is the ultimate irony. We once believed that matter was everything and void was nothing. Now we know that matter is a minority and void is the majority. The vacuum, the spaces between, is the true ruler of the cosmos. Gravity, which we thought belonged only to massive objects, is in fact written into the very fabric of empty space. It is difficult to imagine, but the equations leave no doubt. Nothing is heavy. Nothing has weight. And it is this weight of nothing that may decide how everything ends. Between prediction and observation lies a gulf of more than 100 orders of magnitude, the greatest mismatch in all of science. This is the puzzle of dark energy. We know it exists, we measure its effects, but we do not understand its origin. Is it truly a cosmological constant, a property of space itself, unchanging across all time? Or is it a field, dynamic and evolving, shifting as the universe grows? Some theories imagine quintessence, a mysterious field that permeates space, changing slowly over cosmic history. Others suggest that gravity itself may need revision on the largest scales. Yet, whatever the answer, the fact remains that nothing, empty space, has become the central player in cosmology. This realization humbles our earlier understanding. We once thought of the cosmos as a grand arena filled with galaxies, stars, and planets with emptiness between them. Now we know the arena itself is alive, and the emptiness is heavier than the players. More than 2/3 of the universe is dark energy. Matter, the stuff of atoms and galaxies, makes up less than 1/3. The stars we see are mere sparks on the surface of a sea whose depths are invisible. And yet this invisible sea commands everything. It shapes the past. It governs the present. It decides the future. If the cosmological constant remains steady, the universe will drift into cold eternity. If dark energy grows stronger, the cosmos will be torn apart in violence. If it fades, the expansion may one day reverse into collapse. The universe's destiny is written not in the mass of galaxies, but in the pressure of emptiness. To speak of gravity without mass is strange, but here it is undeniable. Nothing has become the most powerful form of something. The void bends spacetime. The vacuum pushes galaxies apart. The weight of emptiness has become the architect of the cosmos. This truth brings us to the very edge of imagination. If the vacuum can curve spacetime, then perhaps even geometry itself is woven from deeper principles we do not yet grasp. Perhaps what we call empty is only a shadow of hidden fields or dimensions. Perhaps the true foundation of gravity lies not in mass, not in energy, not in emptiness, but in some principle beyond our current vision. For now we stand with the paradox. Nothing has weight, nothing pulls, nothing pushes, nothing shapes the universe. The gravity of nothing is not absence but presence, not silence but command. And from this silence we step forward to another revelation. If even nothing can carry gravity, then perhaps waves of pure curvature traveling without mass or matter can also exist. Gravity itself may move as a ripple, carrying energy across the cosmos with no mass at all. The next step in our journey leads us to these ripples, the gravitational waves that prove once again that gravity belongs not only to matter, but to the very fabric of spacetime itself. It is difficult to imagine that the universe itself can shiver. Yet, this is exactly what Einstein's theory predicted. In his general relativity, spacetime is no longer a rigid stage, fixed and unmoving. It is a living fabric, flexible and dynamic, responding to matter and energy, shaping the trajectories of stars, planets, and light. And like any fabric under stress, it can ripple. Those ripples are gravitational waves, and they carry energy not as particles, not as mass, but as pure oscillations of geometry. They are the most delicate tremors the cosmos can send. Yet they hold the power to tell us of the most violent events in existence. The concept itself arose naturally from Einstein's equations in 1916. He realized that if masses accelerate, if they orbit, collide, or collapse, they should disturb the fabric of spacetime, and the disturbance would travel outward at the speed of light. Just as ripples spread across a pond after a stone is thrown, these waves would not be made of matter or light, but of the geometry itself, stretching and squeezing as it moved. They would be pure curvature, massless, yet carrying energy across unimaginable distances. At first, even Einstein doubted whether such waves were real. The mathematics allowed them, but the effect seemed so weak that no instrument could ever detect them. Some physicists argued that they were mere artifacts of the equations, mathematical illusions with no physical reality. Yet others insisted that if relativity was correct, then gravitational waves must exist. The debate persisted for decades, with the waves living in a twilight between possibility and certainty. Hints came not from laboratories on Earth, but from the heavens. In the 1970s, two astronomers, Russell Hulse and Joseph Taylor, discovered a remarkable system. Two neutron stars locked in orbit around one another, spinning with unimaginable density. Careful timing of the pulsar signals from one star showed that the orbit was shrinking. The stars were spiraling inward, as though losing energy to something unseen. The rate of shrinkage matched Einstein's predictions perfectly. The system was radiating energy in gravitational waves, and though we could not yet hear them directly, we could see their fingerprints in the slow dance of dying stars. For this discovery, Hulse and Taylor won the Nobel Prize, and gravitational waves moved from speculation to serious expectation. Still, the waves themselves remained elusive. To detect them directly, scientists needed an instrument so sensitive it could measure distortions smaller than the width of a proton across kilometers of space. The challenge seemed impossible. But across the latter half of the 20th century, engineers and physicists worked to build such a device. Their idea was to use light itself as a ruler, splitting laser beams into long perpendicular arms, reflecting them back with mirrors, and recombining them to see if spacetime had stretched or squeezed by the passage of a wave. This was the principle behind LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO was an audacious gamble. 2 detectors, one in Washington state and the other in Louisiana, were built with arms 4 kilometers long. They were designed to measure distortions of spacetime as small as 1 part in 10 to the power of 21. That is a fraction so small that if you were measuring the distance to the nearest star, it would correspond to less than the width of a human hair. For years, the detectors listened, waiting for spacetime to ring. The noise was immense. Trucks on distant highways, storms rolling across the land, even the faint seismic hum of the Earth itself. To hear the universe above this din seemed like trying to catch the whisper of a butterfly in the middle of a hurricane. And yet, in September of 2015, the whisper came. 2 black holes more than 1 billion light-years away spiraled together, colliding in a storm of unimaginable violence. In the final seconds of their dance, they converted a mass 3 times that of the Sun directly into energy, not as light, not as particles, but as gravitational waves. Those waves traveled across 1 billion years of space, growing weaker with distance until they reached Earth. They stretched and squeezed spacetime itself as they passed, and the twin detectors of LIGO trembled in unison. The signal was unmistakable. A rising chirp, the death cry of 2 merging black holes written in the language of spacetime. Humanity had heard the universe sing. This was more than detection. It was confirmation that gravity can exist without mass, carried not by particles but by ripples of geometry itself. The waves were massless, yet they bore immense energy, enough to outshine all the stars in the observable universe for the brief moment of collision. In that instant, the cosmos revealed that energy without matter could shake the very fabric of reality. Einstein's ghost, once doubting, was vindicated. The discovery marked the dawn of a new astronomy. For centuries, we had studied the universe through light. First with our eyes, then with telescopes that extended vision into the realms of radio waves, X-rays, and gamma rays. But gravitational waves opened an entirely new sense, a way of hearing the universe through its deepest vibrations. Where light can be blocked by gas and dust, gravitational waves pass through unscathed. Where light cannot escape the grip of a black hole, gravitational waves carry the story of its birth. For the first time, we could observe the invisible, not by sight, but by touch, feeling the tremors of space-time itself. And so gravitational waves stand as the purest expression of the question we have been following. Can gravity exist without mass? The answer flows through the detectors, through the trembling of mirrors, through the rising chirp of colliding black holes. Gravity can travel, massless and free, carrying energy across the cosmos as waves of pure curvature. The weight of nothing has become a voice, and spacetime itself has learned to sing. The first direct detection of gravitational waves was not the end of the story, but the beginning of an entirely new chapter in humanity's exploration of the cosmos. When the chirp from those 2 colliding black holes reached Earth, it was more than a signal. It was proof that spacetime is not rigid, but alive, capable of vibration. That chirp lasted only a fraction of a second, but within its brief rise and fall was encoded the entire drama of 2 black holes spiraling toward destruction. Their masses, their spins, their distance, even the moment of their merger. All of it was written into the shape of the wave. For the first time, scientists could reconstruct the hidden ballet of black holes without ever seeing them in light. This changed astronomy forever. Until that moment, every discovery of the universe had been made through particles, photons of light, neutrinos, or cosmic rays. Each particle traveled across the cosmos, carrying information from its source, but each could be scattered, absorbed, or blocked. Light cannot penetrate dense clouds of gas. Neutrinos are ghost-like, but almost impossible to detect in large numbers. Cosmic rays are bent and scrambled by magnetic fields. Gravitational waves, by contrast, pass through everything. They do not scatter. They do not dim. They are not deflected. They are pure vibrations of space-time, arriving exactly as they were created, no matter how far they have traveled. This means that gravitational waves give us access to regions of the cosmos that were once hidden. We can hear the collisions of black holes that emit no light. We can probe the interiors of neutron star mergers where light is swallowed. We can trace the collapse of massive stars into black holes, even if their explosions are shrouded in gas. We are no longer limited to seeing the universe. We can listen to it. The metaphor is not poetic flourish. Gravitational waves literally produce a signal that can be translated into sound. The chirp detected by LIGO was converted into audio, and one can hear the rising tone as the black holes spiral inward. It is faint, but it is the voice of space-time. That first sound was humanity's entry into gravitational wave astronomy, a discipline that now promises to uncover secrets unreachable by any other means. Since the first detection, dozens of gravitational wave events have been recorded. Black holes merging with black holes, neutron stars colliding with neutron stars, even black holes swallowing neutron stars. Each has left its mark upon the detectors. Every event has expanded our understanding. We now know that black hole mergers are more common than once imagined. We now know that neutron-star collisions forge heavy elements like gold and platinum, seeding the universe with the materials that eventually build planets and life. We have confirmed that gravitational waves travel at the speed of light. As relativity predicted, each discovery tightens the bond between theory and reality. The scale of energy involved in these events is staggering. When two black holes collide, they release more energy in gravitational waves in a fraction of a second than all the stars in the observable universe emit in light during the same time. Yet those waves spread so thinly across space that by the time they reach Earth, they stretch space-time by less than the width of a proton. The fact that we can detect them at all is a triumph of human ingenuity, a reminder that the tools of science can capture even the faintest tremors of reality. What makes gravitational waves so profound in the context of our question is that they are gravity without mass in its purest form. They are not tied to particles. They are not the pull of one object upon another. They are the propagation of curvature itself. They demonstrate that gravity is not merely a static warping of space around mass, but a dynamic, living phenomenon that can carry energy across the cosmos without any material medium. This realization reshapes our intuition about gravity. For centuries, we thought of it as a force pulling masses together, then as a curvature shaped by energy and matter. Now we must also see it as a wave, a vibration that needs no mass to exist. Gravity is not confined to objects. It can leave them behind and travel independently. It is geometry itself in motion. And with this new way of observing, we begin to dream of what might yet be discovered. Could we hear the echoes of the Big Bang? Primordial gravitational waves still ringing from the birth of the cosmos. Could we detect waves from cosmic strings, hypothetical defects in space-time itself? Could we one day build detectors sensitive enough to hear the whispers of space-time across the entire history of the universe? The answers to these questions lie in the future, but the path is now open. we have crossed the threshold into a universe where gravity is not only a silent shaper of orbits, but a messenger, a traveler, a wave without mass that speaks to us across billions of years. The arrival of gravitational wave astronomy has changed more than our instruments. It has altered our imagination of what the universe truly is. For centuries, humanity relied upon sight. We built telescopes to extend our vision, catching photons of every wavelength, from radio waves that map the cold hydrogen of galaxies to gamma rays that capture the most violent bursts of energy. But all of these belong to the same family. They were messengers of light, carriers of electromagnetic information. Gravitational waves are different. They are not particles traveling through space-time. They are space-time itself in motion. To hear them is not to listen to a message from within the universe, but to listen to the universe itself. This distinction changes how we think about what it means to observe. When we catch photons, we see surfaces. The light from a star comes from its photosphere, the thin layer where it becomes transparent. The light from a galaxy comes from its shining stars, not from its hidden interior. Photons cannot escape from the heart of a black hole, and they cannot travel unimpeded through dense matter. Gravitational waves, by contrast, emerge from the depths. When two black holes merge, they do not send us light. They cannot. But they do send us ripples of curvature that travel unblocked across billions of light years. We do not see their surfaces. We feel their very merger. This power makes gravitational waves a probe of the invisible. They tell us about masses we cannot otherwise detect, about collisions we cannot otherwise see. They reveal black holes that were once silent, hidden in darkness. They show us neutron stars colliding, creating kilonovae, whose light is faint, but whose space-time tremor is unmistakable. They carry direct evidence of the processes that forge the heavy elements, confirming that gold, platinum, and uranium were born in cosmic collisions. With each new detection, we add to the story of matter's origin, and with it our own. Perhaps most striking is how gravitational waves reaffirm the core lesson of relativity. Mass is not the only source of gravity, and gravity is not limited to mass. Here we encounter gravity traveling without mass at all. The waves themselves are not made of particles, yet they carry energy. They have no rest mass, yet they influence detectors on Earth with physical force. They can shake mirrors, alter distances, and deposit energy into matter. Gravity is not confined to matter. It is an active participant in the cosmos, able to detach from its sources and propagate on its own. This is the clearest proof of our central question. Can gravity exist without mass? Gravitational waves are the answer, rippling across space-time with no particles, no rest mass, yet undeniable in their effects. They are energy in motion, born of the collapse and collision of massive bodies, but freed into pure curvature. They are geometry turned into music, massless but powerful, and this music carries secrets that may one day reach to the beginning of time itself. The expansion of the universe after the Big Bang may have generated primordial gravitational waves, ripples imprinted upon space-time when it was less than a trillionth of a second old. Unlike light, which could not escape until the universe cooled enough to become transparent, gravitational waves from that first instant would still be traveling today. Detecting them would mean listening to the birth cry of the cosmos, a sound older than any star, older even than atoms. If we can hear it, we may glimpse physics beyond anything known, the unification of forces, the birth of space-time itself. There is also the possibility of hearing waves from phenomena we have not yet confirmed. cosmic strings stretching across the universe, vibrations of extra dimensions, or the resonances of spacetime itself at the quantum level. Each detection would not merely add a detail, but open a new chapter in our understanding of reality. The fact that such possibilities exist at all shows how radical gravitational waves are. They are not only another kind of astronomy, they are a new way of touching the foundation of existence. And so the story of gravitational waves brings us back to our guiding theme. Gravity is not bound to matter. It can travel without substance, carry energy without particles, and shape the universe in forms our senses cannot imagine. Gravitational waves prove that geometry itself can move, that spacetime is not passive but dynamic, and that the pull we feel beneath our feet is only one face of a far greater reality. As we close this chapter, the message is clear. Gravity without mass is not speculation. It is a fact written into the detectors on Earth, into the chirps of merging black holes, into the stretching of spacetime itself. It is a fact that has transformed physics, astronomy, and our vision of the cosmos. Gravity can sing, and it sings without mass. The next step in our journey brings us back to the familiar, but now with deeper understanding. For all its strange manifestations, gravity is still most familiar to us through mass, through planets, stars, and black holes. And while energy in all its forms can bend spacetime, mass remains the most visible and intuitive source. To see why, we must return to the empire of mass, where gravity rules with overwhelming power, shaping the largest structures and the most extreme objects. For all that we have discovered about energy, light, pressure, and even emptiness as sources of gravity, there remains a truth that is both humbling and familiar. Mass still dominates our experience of the cosmos. When we stand upon the Earth, what holds us is the mass of rock and metal beneath our feet. When we look to the sun, what binds the planets to their paths is the overwhelming pull of its mass. When galaxies spin and clusters form, when black holes collapse, it is mass concentrated into staggering density that shapes the fate of stars and systems. Energy may be the more general source, but mass is its most tangible and commanding form. The story of mass and gravity is an ancient one. Newton gave us the law of universal gravitation, describing how every mass pulls on every other with a force proportional to their product and inversely proportional to the square of their distance. This was the first universal law, one that explained falling apples and orbiting moons in a single sweep. In Newton's vision, mass was both the source and the subject of gravity. It was what pulled, and it was what was pulled. The theory worked so well that for centuries it defined our intuition. Even today, when we speak casually of gravity, what we mean is mass attracting mass. Einstein replaced Newton's force with the curvature of spacetime, but he did not erase the centrality of mass. Instead, he expanded it, showing that mass is only one form of energy among many. Yet in the everyday world, where velocities are small compared to the speed of light and pressures are tiny compared to those inside stars, mass is the dominant entry in the stress-energy tensor. It overwhelms pressure. It dwarfs radiation. It outshines the vacuum's whisper. For human beings walking upon a planet, for engineers building satellites, for astronomers charting orbits, mass remains the simplest and strongest source of gravity. Consider the Earth. Its gravity is not noticeably influenced by the energy of sunlight or the pressure of its atmosphere. These effects are present, but they are vanishingly small compared to the mass of the planet itself. The Earth bends spacetime because it contains 5.97 times 10 to the power of 24 kilograms of matter, not because of the energy of its weather systems. The moon circles the Earth because of that mass. Tides rise and fall under its pull. Our sense of up and down, our very definition of weight, are dictated by mass. The same is true at the scale of stars. The sun's radiation contributes to its gravity, but its mass dominates by far. The orbits of planets are determined almost entirely by the sun's 2 × 10 to the power of 30 kilograms of matter. That mass bends spacetime deeply enough to hold an entire planetary system in place for billions of years. Light streams outward. Pressure pushes against collapse. But it is mass that makes the solar system possible. Black holes take this to the extreme. They are the purest examples of mass energy concentrated into geometry. When a star collapses beyond the ability of pressure to resist, its mass curves spacetime so steeply that nothing can escape. A black hole is not made of matter in the ordinary sense. It is an event horizon, a boundary beyond which mass and energy are trapped. But its gravitational pull is described entirely by its mass, its spin, and its charge. In black holes, mass rules absolutely. The waves we detect from their collisions are born of their motion, but the depths of curvature that create them are carved by mass compressed into a point. Even at the largest scales, mass remains central. Galaxies form as clouds of matter collapse under their own pull. Clusters of galaxies are bound together by the mass of both visible matter and the mysterious dark matter that outweighs it. The cosmic web, the grand structure of the universe, is a map of where mass has pulled and gathered across billions of years. Radiation and pressure shaped the early stages, and dark energy drives the expansion today. But the intricate filaments and knots of galaxies are the handiwork of mass. This does not diminish the other sources of gravity we have explored. Instead, it places them in context. Energy in all its forms bends spacetime. But mass is the most concentrated, the most familiar, the most immediate. It is the form of energy we can touch and weigh. It is the form that dominates the lives of stars and planets, the form that shapes the geometry we navigate every day. Mass may not be the whole story, but it is still the headline. And yet, even as we acknowledge the empire of mass, we must keep in mind that it doesn't rule alone. It is first among equals in the ledger of energy, but the others are always present, always shaping the cosmos in ways we do not always see. Gravity is not only mass, it is energy, pressure, momentum, stress, and even nothingness. Still, when we look up at the night sky, when we feel the pull of Earth, when we study the collapse of stars, mass remains the most visible face of gravity. The question then is not whether mass is important. It unquestionably is, but whether gravity can exist without it. We have seen that it can in the push of light, in the pressure of radiation, in the weight of nothing, and in the ripples of space-time itself. But the dominance of mass reminds us that while gravity is broader than we imagined, it is also simpler. At its heart, space-time responds to energy, and mass is simply the most concentrated form of that energy. To reconcile the familiar with the strange, we must accept both truths at once. Mass rules where it is present, but it does not rule alone. The cosmos bends to all forms of energy, but it bends most deeply to mass. The empire of gravity is shared, and its throne is broad. As we carry this understanding forward, we turn to the next question. If we know that energy in all its forms can create gravity, could humanity ever generate it without relying on mass? Could we build devices that bend space-time with beams? Of light or fields of energy, or the vacuum itself? Could we create gravity in the laboratory, not by piling up matter, but by summoning curvature through other means? The challenge seems immense, but the thought demands pursuit. When we speak of the dominion of mass, we speak not only of planets and stars, but of the hidden matter that pervades the cosmos. For even mass itself has a mystery. The luminous matter we see, the stars burning in galaxies, the gas clouds drifting between them, the dust that seeds planets, makes up only a small fraction of the universe. The rest is hidden in shadows. Observations of galaxies show that their stars orbit too quickly to be held by visible matter alone. Gravitational lensing reveals invisible mass bending the paths of light from background galaxies. The large-scale structure of the universe requires a foundation of unseen weight. This is dark matter, a form of mass we cannot see, but that outweighs the visible by nearly 5 to 1. Dark matter reminds us that mass is not only what we can touch or see, but what space-time records. Whatever its nature, particles yet undiscovered, exotic relics from the early universe, or something stranger still, dark matter is mass in the sense that matters most. It bends space-time. It sculpts galaxies. It anchors clusters. It is silent, invisible. But in its gravitational rule, it is undeniable. When we speak of where mass still dominates, we must include this hidden empire. Without it, galaxies would fly apart. The cosmic web would dissolve, and the universe we inhabit would not exist. Yet, dark matter is not the only way in which mass asserts its dominance. At the level of black holes, mass rules with an intensity beyond imagination. These objects are the epitome of mass concentration, regions where pressure, light, and all other forms of energy have collapsed into a singularity. The event horizon is the boundary of no return, and what defines its size is the mass contained within. A black hole of 10 solar masses has a horizon of only a few tens of kilometers, while one of a billion solar masses can rule the heart of a galaxy. In each case, the geometry is defined by the mass, its influence stretching far beyond the horizon, bending space-time so strongly that even light cannot escape. And black holes do not merely sit in isolation. They collide, merge, and grow, shaping galaxies themselves. At the centers of most galaxies lie supermassive black holes, millions to billions of solar masses in scale. Their pull dictates the motions of stars in their vicinity. Their growth influences star formation. Their mergers send gravitational waves rippling across the cosmos. Though light and energy have their role, the sheer dominance of mass in these monsters shows why gravity still belongs most intuitively to matter. But the rule of mass is not only cosmic. It defines our daily lives. When an apple falls from a tree, it is mass responding to mass. When tides rise and fall, it is the pull of the moon's mass upon Earth's oceans. When satellites orbit, they obey the curvature defined by Earth's mass. Mass is the form of energy most accessible to our senses. It is why we can weigh, why we can measure, why we can build. Pressure, light, and stress may curve space-time, but they are abstract to us. Mass is immediate. This immediacy explains why Newton's view held so long, why our intuition remains bound to it. Mass can be felt in our muscles when we lift, in our steps when we climb, in our bones when we stumble. No one feels the weight of a photon or the pressure of radiation directly, but everyone feels the weight of mass. It is woven into our instincts. And even though Einstein showed us that gravity is more than mass, our senses still whisper the Newtonian tale. Yet there is also a philosophical lesson here. Mass is not a separate category from energy, but our minds treat it as such because of its dominance in our experience. In the language of relativity, mass is energy at rest, the densest, most concentrated form. That is why it dominates stars, planets, and black holes. That is why it rules our daily lives. But when we step back and see the larger picture, mass is revealed as one form among many, the most visible face of a broader truth. The reign of mass, then, is both absolute and limited. Absolute in our lives, in the orbits of planets, in the binding of galaxies. Limited in that mass does not have exclusive claim to gravity. It shares the throne with light, with stress, with pressure, and with the vacuum itself. To know the whole of gravity, we must keep both truths in mind. And this duality leads us toward the final recognition. Mass may dominate the visible, but energy in all its forms writes the laws. To see what gravity truly is, we must accept the paradox that mass is both central and dispensable. It is central because it defines the structures we see. It is dispensable because the universe can curve even without it. This is the balance of relativity, the coexistence of the intuitive and the strange. From here, the story draws us toward the final frontier of thought. If mass is not required for gravity, could we ever harness this in practice? Could we create measurable curvature in the laboratory without piling up massive objects? Could boxes of light, high-energy fields, or quantum vacuums be used to bend spacetime? These thought experiments belong to the edge of imagination. Yet, they are natural extensions of what we have already learned. To understand why mass still holds pride of place in our story, we must return to the scale of the cosmos itself. When we map the distribution of galaxies across billions of light years, what we see is a web-like structure with filaments stretching across vast distances and clusters forming at their intersections. This cosmic web is not shaped by light or by pressure. It is carved by mass, both visible and dark. The gravitational pull of mass gathered into filaments draws more matter toward it, amplifying the structure over time. Radiation played its part in the early universe, and dark energy drives the expansion today. But the intricate architecture of galaxies is a monument to mass. Even in galaxy clusters where temperatures soar into the tens of millions of degrees and radiation floods the space between galaxies, it is still mass that rules. The hot plasma radiates X-rays, and the light of thousands of galaxies pours into the void. But the motions of the cluster are governed by mass, most of it invisible. Observations of these clusters reveal that more than 80% of their total weight is dark matter, a silent but irresistible anchor. Light fills the void, but mass binds it. And when we look deeper still into the engines of galaxies, we find once again that mass is sovereign. The supermassive black holes at galactic centers dominate their surroundings. Their mass bends spacetime so deeply that entire stellar systems orbit around them. They consume matter and flare with energy. But it is their mass that defines the geometry of their horizons. No amount of radiation or pressure could mimic their pull. In black holes, mass shows its most extreme form, reducing all else to silence. The role of mass in our daily lives is no less absolute. The gravity that shapes tides, that governs orbits, that defines weight, is all determined by mass. The fact that we live upon a planet, orbit a star, and exist in a galaxy is owed to the overwhelming presence of mass. It is this immediacy that keeps our intuition bound to Newton's picture. Even though relativity has shown us that energy in every form curves spacetime, the world we inhabit reminds us daily that mass is the most obvious, the most palpable, the most commanding. Yet the persistence of mass as the central player does not erase the broader truth. It is tempting to imagine that mass is the true ruler of gravity. But Einstein's equations forbid such simplicity. Mass is only one entry in the ledger of energy. And though it dominates where it is present, it doesn't reign alone. Pressure, light, stress, and even emptiness itself must be counted. The cosmos listens to all of them. Gravity is impartial. It bends to every form of energy without prejudice. This duality of mass as dominant but not exclusive reshapes how we think of gravity. On the one hand, mass gives us the strength of gravity we experience every day, the anchor that holds us to Earth, the orbit that binds us to the sun. On the other hand, the universe teaches us that gravity extends far beyond mass. It is written into light, into waves of curvature, into the vacuum itself. We live in the empire of mass. But the empire is part of a larger kingdom. The dominance of mass also hides a subtle irony. For all its rule, mass is itself only energy in another form. It is not fundamental, but emergent. Matter is built of particles whose masses arise from fields, from interactions, from symmetries, broken in the early universe. The Higgs field gives mass to particles, but even here, energy is the true source. Mass is the most familiar and powerful form of energy, but it is not the most fundamental. This recognition closes the circle of our question. Gravity is not about mass alone. It is about energy in every form. And so, while mass still rules in the most obvious ways, in the structures of galaxies, in the pull of planets, in the collapse of stars, it is only part of the story. Gravity can and does exist without it. We have seen how photons can bend space, how pressure deepens curvature, how the vacuum pushes galaxies apart, how gravitational waves carry energy across billions of light years. Mass is the most visible face of gravity, but not its only one. As we step from this recognition, we move toward the frontier of imagination. If mass is not necessary for gravity, could we ever create it without mass? Could we bend spacetime in the laboratory using only energy, light, or fields? Could we engineer gravity from nothing? These are questions that draw us into thought experiments at the edge of science, where theory meets speculation, and where the possibility of creating gravity without matter becomes a tantalizing challenge for the future. The question has lingered since Einstein first expanded Newton's simple vision into the geometry of spacetime. If energy in all its forms bends the fabric of reality, and if mass is only one way of packaging that energy, then what prevents us from creating gravity without piling up massive objects? Could a laboratory experiment, a beam of light, or a field of pure energy create curvature strong enough to detect? Could humanity ever learn not just to observe gravity, but to generate it deliberately, shaping spacetime as easily as we shape light with lenses or sound with speakers? At first glance, the task seems impossible. The pull of gravity is astonishingly weak compared to the other forces of nature. Electromagnetism is so much stronger that a small magnet can lift a paperclip against the entire mass of the Earth. Nuclear forces are stronger still, binding the hearts of atoms. Gravity only dominates on cosmic scales because it is purely attractive, because it never cancels itself out, and because matter is abundant. To replicate its effect in a laboratory without relying on mass requires either enormous energy or exquisite sensitivity. Thought experiments help us imagine how this might be done. Consider a box filled with light. Photons have no rest mass, but they carry energy, and energy curves spacetime. Seal a powerful laser inside a mirrored cavity, and the box should become slightly heavier than the same box without light. Its gravitational field should be correspondingly stronger, though the difference would be unimaginably small. A single laser beam in open space would do the same, bending spacetime along its path. In principle, one could create gravity this way. In practice, the effect would be so tiny that no current detector could hope to measure it. Another possibility lies in radiation pressure and momentum flux. In stars, photons pushing outward help to balance the inward pull of gravity. If we could generate a region of space dominated by radiation pressure, we would generate curvature. Physicists sometimes imagine filling a chamber with an intense photon gas, creating what is effectively a pocket of gravitational influence made entirely of light. The idea is sound, but the required energy density is far beyond anything we can achieve. Even the most powerful lasers on Earth produce effects that are dwarfed by the tiniest gravitational pulls of everyday objects. Then there are the quantum possibilities. The Casimir effect shows that even the vacuum is not empty, but seethes with virtual particles and fluctuating fields. Two conducting plates placed close together feel a slight attraction due to changes in the quantum vacuum between them. This effect is real, measurable, and arises from nothing but the structure of empty space. If the vacuum can push plates together, can it also curve spacetime? In principle, yes. The vacuum has an energy density, and according to relativity, energy density creates gravity. The cosmological constant itself may be nothing more than vacuum energy spread across the universe. Could we harness the Casimir vacuum to generate a pocket of artificial gravity? No one knows. Speculation extends further. Still, some physicists wonder whether high-energy electromagnetic fields could be arranged to create curvature detectable at laboratory scales. Others dream of manipulating the Higgs field or other fundamental fields of nature to create effective masses out of nothing. Still others suggest using superconductors or exotic quantum states of matter to mimic gravitational effects. These ideas are at the edge of what theory allows and far beyond what technology can yet achieve. But they are not forbidden by the laws of physics. The challenges are immense. To create gravity strong enough to measure without mass would require energy densities far beyond anything humanity has ever concentrated. The energies of particle colliders, powerful as they are, vanish compared to the binding energy of a planet or the collapse of a star. Yet, even if we cannot generate gravity artificially, exploring the possibility sharpens our understanding of what gravity really is. It forces us to confront its origin in energy rather than mass. To think of it not as an invisible tether, but as the shape of spacetime itself, responding to every form of existence. The thought experiments remind us of something deeper. If we cannot yet create gravity without mass, the universe itself already does. Black holes radiate gravitational waves, massless yet powerful. Stars balance mass with photon pressure. The vacuum drives cosmic expansion. Everywhere we look, energy without matter shapes the cosmos. Humanity may not yet wield this power, but nature already demonstrates it on every scale. And so the pursuit of creating gravity without mass is less about building machines and more about understanding the principle. It is about recognizing that gravity is not confined to the tangible weight of matter, but is written into the essence of energy. Whether we can ever control this fact is uncertain, but knowing it changes how we see reality. It tells us that gravity is not merely the pull of planets and stars, but a universal language spoken by light, by fields, by the vacuum, and perhaps one day by our own experiments. The dream of creating gravity without mass draws us into a landscape of both science and imagination. For while our instruments are not yet capable of bending spacetime on command, our theories insist that the boundary between the possible and the impossible is thinner than we think. When Einstein wrote down his equations of general relativity, he left no exemption for human technology. If energy curves spacetime, then in principle any energy, no matter its form, could be harnessed. The question is not whether it is allowed, but whether we can ever gather enough of it in the right way to make the effect noticeable. One of the simplest thought experiments begins with a beam of light. A single photon has no rest mass, but it carries momentum and energy. Fire a laser across a room, and the beam ever so slightly curves the spacetime through which it travels. The effect is so small that it vanishes beneath all noise. But in theory, it is there. Now imagine an unimaginably powerful laser, one capable of filling a chamber with a photon gas as intense as the radiation inside a star. The energy density would be enormous. According to relativity, this would create a small but measurable curvature. A mirror box filled with such radiation would weigh more than the same box empty. Light would be bending spacetime, and in doing so, light would create gravity. The challenge is scale. Even the strongest lasers built today, firing petawatts of energy in pulses measured in femtoseconds, produce gravitational effects so small they might as well not exist. The energy required to produce noticeable curvature would rival the total output of stars. For now, such experiments belong to science fiction. And yet, they sharpen the imagination. They remind us that in the deepest sense, mass is not necessary. What we call mass is simply the most familiar concentrated form of energy. Other proposals push into the realm of quantum physics. The Casimir effect, measured with exquisite precision, shows that vacuum fluctuations have real consequences. The plates of a Casimir experiment feel an attraction not because of hidden matter, but because of the vacuum's restless energy. If vacuum energy can push, then by relativity, it must also bend. The cosmological constant may be a manifestation of this on cosmic scales, with the vacuum of space itself driving galaxies apart. Could a laboratory Casimir experiment ever produce detectable curvature? The forces are tiny, but if we learn to manipulate vacuum energy, the possibility cannot be excluded. Some have speculated about exotic states of matter that might mimic gravitational effects. Superconductors with their strange quantum coherence have been rumored in speculative research to produce anomalies in gravitational measurements, though no robust evidence has ever emerged. Others suggest that intense magnetic fields might couple to spacetime in unexpected ways. These ideas live at the edges of physics, controversial and unproven, but they speak to a desire that runs deep in human thought. The desire not only to measure the cosmos, but to shape it. It is important to remember that even if we never succeed in creating artificial gravity, the universe already demonstrates it for us. Gravitational waves are generated not by mass in the ordinary sense, but by the energy of motion and collapse. Radiation pressure inside stars contributes to their gravitational fields. The vacuum itself accelerates the expansion of space. Gravity without mass is not only possible, it is happening everywhere all the time. Our thought experiments are reflections of what nature has already perfected. And yet there is something uniquely human in imagining these possibilities. For centuries, we dreamed of flight until we learned to harness the principles of lift. We dreamed of reaching the moon until rockets carried us there. We dreamed of splitting atoms until we mastered the nucleus. Each of these once seemed impossible, yet each became reality when theory met technology. Perhaps one day the manipulation of space-time itself will follow the same path. The implications would be staggering. Artificial gravity fields could revolutionize space travel, freeing astronauts from the harmful effects of weightlessness. Curvature could be engineered to bend light in ways surpassing any lens, opening possibilities for communication, imaging, and even cloaking. At its most speculative, control over gravity could reshape energy itself, tapping into reservoirs hidden in the geometry of space-time. Such visions are distant, but they are not forbidden by the laws of physics. They wait upon our ingenuity. For now, the experiments remain beyond our reach. But the pursuit itself enriches our understanding. Each attempt forces us to refine relativity, to test its boundaries, to explore the relationship between energy fields and curvature. Each thought experiment deepens our intuition, helping us to see that gravity is not only the domain of mass, but of all existence. And so the question of creating gravity without mass remains unanswered in practice, but answered in principle. We cannot yet build machines that bend space-time with beams of light or fields of vacuum. But we know it is possible because the universe itself does it for us. Every photon, every fluctuation, every wave of curvature is a reminder that gravity belongs not only to matter, but to energy itself. The challenge ahead is not to prove this truth, but to learn whether we can ever harness it. The pursuit of creating gravity without mass leads us into a place where science, philosophy, and imagination converge. We know the principles. Einstein's equations do not distinguish between energy stored in matter and energy stored in light, fields, or vacuum. Every form contributes to curvature. The question is whether we, as beings of limited scale, can ever marshal enough energy in the right configuration to bend space-time in a way we can control. This question is not only technical, but existential, for it forces us to confront our role in the cosmos. Are we forever observers of gravity? Or can we become its sculptors? History suggests caution. Humanity has often dreamed ahead of its means, envisioning powers long before technology could deliver them. In the 19th century, writers imagined voyages to the moon and machines that could fly, while engineers still struggled to build reliable steam engines. In the early 20th century, physicists speculated about splitting the atom long before accelerators revealed the nucleus. Today, we stand in a similar place with gravity. We know it is possible in principle to generate curvature without mass. We can even describe how it would work with boxes of light, with quantum vacuums, with immense fields. But the energy scales required are staggering. Far beyond our present reach, the difference between principle and practice stretches wider than the gap between a dream and a rocket. Still, the very act of asking reshapes our view. For centuries, gravity was imagined as the most rigid of forces, the immutable background of all motion. Now we know it is pliable. We know it can ripple, bend, and stretch. We know it can be generated not only by planets and stars, but by light and stress. We know the vacuum itself can give it weight. In this recognition, gravity transforms from a passive stage into an active medium, a field that responds to all existence. To imagine shaping it is to imagine engaging with the universe at its most fundamental level. Even if laboratory control proves forever impossible, the universe has already answered the question for us. When neutron stars collide, they release bursts of gravitational waves, waves of pure energy with no mass attached. When light streams outward from the sun, its radiation pressure curves space-time alongside the mass that generates it. When the vacuum drives cosmic acceleration, empty space itself becomes a gravitational actor. In these examples, we see gravity without mass, not as a speculation, but as a fact. We may not yet wield it, but we live within its reach. And so the idea of creating gravity without mass becomes a mirror. It reflects back to us our curiosity, our ambition, and our humility. It shows us that nature is already doing what we dream of on scales far larger than we can imagine. It reminds us that our place is not only to master, but to understand. To know that gravity is broader than mass is already to see deeper into the universe than any of our ancestors could. To know that space-time itself is alive with energy and curvature is already to walk among the giants of thought. Yet, it is also a call to the future. Technologies once thought impossible have been achieved. Dreams once dismissed as fantasy have been realized. If energy and ingenuity continue to grow, if theories guide us toward breakthroughs, perhaps one day humanity will bend space-time. Not only by accident, but by design. Perhaps artificial gravity fields will one day hold spacecraft together, not with spinning habitats, but with engineered curvature. Perhaps beams of light will one day sculpt space-time as easily as lasers sculpt patterns of illumination today. Perhaps the dream of creating gravity without mass will pass from speculation into history, as other dreams have before. But even if it never comes, the lesson remains. Gravity is not owned by mass. It is not limited to the pull of matter. It is written into the fabric of energy itself in all its forms. The cosmos bends and sways, not only to the weight of planets and stars, but to the presence of light, of fields, of pressure, of vacuum. To ask whether we can create gravity without mass is to acknowledge that mass is not the true essence. Energy is, and gravity is the shape that energy writes upon space-time. Thus, the chapter closes with both humility and wonder. We may never hold in our hands the ability to sculpt gravity as we sculpt light, but we already know enough to see that gravity does not require mass. It requires only energy, and energy is everywhere. The universe itself is the laboratory, the proof, the answer. From here we move to the final reflection. We have traveled through the domains of mass, of light, of pressure, of vacuum, and of waves. We have asked whether gravity can exist without matter and found that it can. The last step is to gather these threads, to see the pattern they weave, and to offer a final word on what gravity truly is. We began with a question that seems simple, almost naive. Can gravity exist without mass? The instinctive answer is no. We feel gravity when we stand on the Earth. We see it in the orbits of the planets around the Sun. We witness its extremes in the collapse of stars into black holes. Gravity feels inseparable from mass. The weight that holds us to the ground, the substance that shapes worlds. Yet, as we have followed the threads of Einstein's vision, we have uncovered a deeper truth, one that overturns the comfort of intuition. Gravity is not the servant of mass alone. It is the response of space-time to energy in every form. The journey has carried us far. We began with Newton's simple law, where mass attracts mass with invisible force. We moved to Einstein's curvature, where mass bends space-time and tells matter how to move. We discovered that light, though massless, curves space by carrying energy. We found that photons trapped in stars or mirrored boxes contribute to gravity. That pressure and stress are as much a part of the equation as weight. That even the vacuum itself has energy enough to expand the universe. We listened to the ringing of space-time in gravitational waves, ripples carrying energy without particles, born in collisions more violent than any other. Again and again, the answer returned. Yes, gravity can and does exist without mass, and yet mass remains the most familiar and commanding source. It is the form of energy we live with, the face of gravity we experience daily. Planets and stars bend space-time most clearly through their mass. Black holes embody it to extremes, ruling their surroundings with geometry, carved by pure concentration of matter. Galaxies form and hold together because mass, both visible and dark, binds them. In the universe we see, mass dominates not because it is exclusive, but because it is abundant. It is the loudest voice in the chorus, though not the only one. So what then is gravity? It is not a pull between masses, nor even simply the curvature of space-time by matter. It is the geometry written by energy in every form and every place. It is the shape of reality itself, responding to light, to pressure, to momentum, to vacuum, to waves, to everything that exists. It is not limited to the weight of planets and stars. It belongs also to the radiance of photons, to the tremors of space-time, to the whisper of the void. The final word, then, is both simple and profound. Yes, gravity can exist without mass, but no, it can never exist without energy. The distinction is more than semantics. It changes our vision of the universe. It tells us that mass is only one part of a broader tapestry, that the cosmos bends and sways not only to what we see and weigh, but to what we cannot touch, to what we once thought of as nothing at all. This recognition is not the end, but a beginning. Gravitational wave observatories now listen to the universe through its vibrations. Future experiments may one day probe the vacuum itself for signs of curvature. Theories at the edge of physics seek to merge gravity with the quantum, to explain how space-time itself emerges from deeper principles. In all of this, the idea that gravity requires mass will no longer suffice. We must embrace the larger truth. Gravity is the shape of energy, and energy is the essence of existence. Stand for a moment beneath the night sky and let this truth settle. The pull you feel underfoot comes from Earth's mass. The orbit that carries you around the sun is carved by matter gathered into a star. But the very expansion of the universe around you is driven by the weight of the vacuum. The galaxies you see are held by invisible dark matter. The cosmos itself trembles with waves of pure curvature. Gravity surrounds you not only as the pull of matter, but as the music of energy in all its forms. So the answer to our question is not only yes, but more than yes. Gravity without mass is not a rare exception. It is the rule, the reality, the way the universe works. Mass is only the most visible expression of a truth far deeper. Gravity is not the pull of matter. It is the shape of reality itself written by everything that exists, even light, even nothing. If the essence of gravity is energy rather than mass, then what does that mean for our understanding of the universe? To see the implications clearly, we must revisit the familiar picture we hold of reality. Most of us imagine the cosmos as made of things: planets, stars, galaxies, clusters, collections of matter shaped by invisible forces. But the deeper truth, revealed by relativity and by all the discoveries since, is that the universe is not a collection of objects on a background. It is a living fabric woven of energy in all its forms, with space-time as both stage and actor. Gravity is not a tether between things, but the shape of this fabric itself. This reshapes the questions we ask. When we ask how galaxies hold together, We are not only asking about the mass they contain, but about how space-time bends in response to hidden dark matter. When we ask how the universe expands, we are asking how the vacuum's energy curves geometry on the largest scales. When we study black holes, we are not asking how much matter sits at their centers, but how space-time organizes itself. When energy becomes infinitely concentrated, the focus shifts from substance to structure, from matter to geometry. And this shift has philosophical weight. For centuries, thinkers debated whether space was a thing or an emptiness. Newton imagined an absolute space, a rigid background on which matter moved. Others, like Leibniz, argued that space was nothing more than relationships between objects. Einstein offered a third path. Space-time is real, but not rigid. It is dynamic, shaped by energy, and it shapes motion in return. In this view, gravity is not a force binding masses together. It is the very geometry of reality. To say gravity can exist without mass is simply to acknowledge that geometry can move, stretch, and ripple even without matter present. This recognition also sharpens the divide between the cosmic and the quantum. On the cosmic scale, relativity reigns, and we see space-time bend under energy. On the quantum scale, fields and particles rule, and energy is carried in discrete quanta. We can describe how photons bend space, how vacuum fluctuations generate forces, how particles exchange energy. But when we try to merge these descriptions, the languages clash. General relativity speaks of smooth geometry. Quantum theory speaks of jittering fields. Somewhere between them lies the full truth of gravity. Not as a force, not even as geometry alone, but as something deeper. It may be that by answering our question, by insisting that gravity does not belong exclusively to mass, we are glimpsing this deeper layer. For if gravity responds to energy in every form, then it is not tied to objects at all. It belongs to existence itself, to whatever reality is made of at its most fundamental level. Whether that level is fields, strings, loops, or something as yet unimagined, gravity will be the shape that level writes upon space-time. The practical consequences are equally profound. We live in an age where gravitational wave astronomy is only beginning. Already we have detected dozens of mergers. Already we have confirmed predictions made a century ago. Already we are learning about black holes and neutron stars. But this is just the first step. Future detectors in space will hear lower frequencies, catching waves from supermassive black holes colliding across billions of light years. Networks of pulsars may reveal background hums from countless mergers across cosmic history. Instruments yet to be built may detect the faint echoes of primordial gravitational waves from the birth of the universe. Each detection will remind us that gravity is not confined to mass, but travels freely as energy itself. Even the expansion of the universe is best understood in this light. Dark energy, mysterious though it is, behaves as a uniform energy density of the vacuum. It is not mass in any sense, yet it curves space-time on the largest scales, accelerating galaxies away from one another. Empty space has weight. The cosmos expands not because of matter, but because of the energy of nothingness. If anything proves that gravity can exist without mass, it is this. The very fabric of space is shaping the universe's destiny without matter's involvement. Thus, when we gather the lessons of relativity, of cosmology, of gravitational waves, of quantum fields, we arrive at a single vision. Gravity is not the property of matter. It is the property of energy. Mass may be its most familiar source, but mass is simply one form of energy and not the deepest. To think otherwise is to mistake the part for the whole. the shadow for the light. This realization humbles us, for it shows that the weight we feel underfoot, the force we call gravity, is only the surface of something vast. It also empowers us, for it reminds us that our minds can reach beyond intuition, beyond instinct, into realms the senses cannot guide. To say that gravity can exist without mass is to say that the universe is broader than it appears. That what bends reality is not only the substance we see, but the energy we cannot. And so in this second step towards the final word, we recognize that our question is not only about physics, it is about perspective. Mass rules our daily lives, but energy rules the universe. Gravity is the story of energy in motion written into spacetime. The next step, the true closing of the circle, is to gather this recognition into a vision of the cosmos that is both scientific and poetic, both precise and expansive, both humbling and inspiring. To close the journey, we must step back and look at the universe with new eyes. We have followed gravity from the weight of the earth to the ripples of space-time, from the push of light to the whisper of the vacuum, from the collapse of stars to the expansion of the cosmos itself. At every turn, we have asked whether gravity requires mass. And at every turn, the universe has answered, no, it requires energy, and energy is everywhere. Consider again the most ordinary of experiences. You stand upon the ground, feeling the pull beneath your feet. It is easy to think of this as the Earth's mass reaching for you, pulling you downward. But what is that mass? It is energy condensed into atoms, fields, and particles, all bound together by the laws of physics. The weight you feel is not mass alone, but the energy of matter arranged into a planet. The Earth bends space-time not because of its substance, but because of its energy content. Even in the simplest experience of weight, the deeper truth is present. Now lift your gaze to the night sky. Every star you see bends space, not only by its matter, but by its radiation, its pressure, its turbulent motions. Galaxies are held together not only by the stars within them, but by oceans of dark matter unseen. Energy in a form we do not yet comprehend. The universe itself is expanding not only because of matter, but because of the vacuum whose energy accelerates the flow of time and distance. Everywhere in every direction, gravity whispers its broader truth. Mass may dominate, but energy rules. The story of gravitational waves crystallizes this in the most dramatic way. When two black holes collide, they convert a portion of their mass into pure energy, carried outward as ripples in space-time. No mass travels across the billions of light-years between them and us, yet their merger shakes the mirrors of our detectors. The signal is undeniable. Space-time can carry gravity without carrying mass. The universe speaks in waves of pure geometry, a music made of curvature. To hear it is to know that mass is not the essence, but only one voice in the chorus. The lesson is scientific, but it is also poetic. Gravity is not the pull of objects upon one another. It is the shape of existence. It is the way energy in all its forms inscribes itself upon space-time. It is the dialogue between what is and the fabric in which it resides. To ask whether gravity can exist without mass is to ask whether the universe can shape itself without matter. The answer written in light, in waves, in vacuum is yes. The universe curves not only for substance, but for energy, even when that energy is hidden, subtle, or empty. This realization changes how we imagine our place. For we are not only creatures bound to the pull of Earth. We are beings immersed in a cosmos where space-time is alive with curvature, tremors, and expansion. We live in a universe that bends not only for matter, but for light, for fields, for nothingness itself. To recognize this is to step beyond intuition into wonder. It is to see gravity not as a chain that holds us down, but as a conversation between energy and reality. And in that conversation lies our future. The instruments we build will listen to gravitational waves from across the cosmos, unlocking stories of black holes, neutron stars, and perhaps even the birth of the universe. The theories we refine will bring us closer to uniting gravity with the quantum, explaining how geometry itself emerges from the smallest scales. The questions we ask will push us beyond mass, beyond matter, into the heart of energy itself. Gravity will guide us not only as a pull, but as a principle, showing us that the universe is deeper than weight, broader than matter, stranger and more beautiful than we imagined. So let the final word be clear. Gravity does not require mass. It requires energy. Mass is only the most familiar form, the one we see and touch. But the true essence is larger. Gravity is the shape of reality itself, written by everything that exists, by matter, by light, by waves, by pressure, by vacuum, by nothing, and everything at once. Stand again beneath the stars and let the thought expand within you. The pull you feel, the orbits above you, the expansion beyond, the waves that pass through unnoticed. All are gravity, all are energy shaping space and time. Gravity is not the servant of mass. It is the poetry of existence, the geometry of reality, the silent music of the cosmos. And it is everywhere waiting to be understood.